Tesla didn't just upgrade a truck. It quietly upgraded the voltage standard for the entire car industry. Cybertruck runs a 48-volt low voltage system where the world has been stuck on 12 volts since the last century. And if you think that's a boring detail, you're about to see why it's the most dangerous kind of disruption. The kind that doesn't trend. The kind that rewrites bills of materials. The kind that forces every supplier to retool. And the kind that can pull more silver into the system without ever saying the word silver. Because the 48-volt shift doesn't just change wires. It changes contacts. It changes relays. It changes the parts where electricity touches metal. And in modern vehicles, silver is the metal of contact used across switches, relays, connectors, breakers, and fuses. So today, I'm going to explain Tesla's silver bomb like a case file. What the 48-volt secret is, why nobody saw it coming, and how a quiet architecture change can ripple into real demand. That isn't branding. That's a warning sign for service techs. This is not your grandfather's 12-volt world. The auto industry is obsessed with new platforms, new batteries, new software. But underneath the marketing, there's a primitive backbone that stayed untouched for decades. The 12-volt system. Motor 1 lays it out bluntly. The industry latched onto 12-volt electrical systems in the 1,950 seconds and largely never changed. Why? Because 12 volts became more than a number. It became an ecosystem. Every supplier built around it. Every technician trained around it. Every connector standard, fuse standard, harness tooling, and test bench built around it. And once something becomes a global ecosystem, changing it is not a decision. It's a war. So the world kept stacking more and more electrical demand on top of a voltage standard designed for a simpler era. And that created a hidden monster inside every modern vehicle, the wiring harness. This is the part of the car you almost never see, but it's one of the most expensive parts to build, one of the hardest parts to assemble, and one of the nastiest parts to service. Because a harness is not wires. A harness is copper mass, connectors, crimps, seal points, routing clips, protection sleeves, testing steps, human labor, human mistakes. And the more features you add at 12 volts, the more copper you buy. Not because engineers love copper, because at low voltage, power means current, and current means thickness. So every new feature in the 12-volt world pushes you toward thicker cables, heavier looms, bigger fuses, and more heat. The harness becomes a profit leak, a weight tax, a complexity tax. So for decades, the industry dreamed about escaping 12 volts, but almost nobody dared to do it in a pure EV, which leads to the moment Tesla snapped the spell. Let's get the facts straight before we get dramatic. Tesla's own Cybertruck manual is explicit. Cybertruck uses a 48-volt lithium-ion low-voltage battery. And it isn't just there as a novelty. Tesla says that 48-volt battery powers windows, doors, touchscreen, and other low-voltage systems when the high-voltage battery is unavailable, and it also provides a redundant source of power for critical systems, such as power steering. So this is not some accessory rail, this is survival power. And that matters because it tells you Tesla's mindset. They're not treating low voltage as a side system. They're treating it like a second backbone. Inside EVs notes the Cybertruck's 48-volt low-voltage system replaces the 12-volt system, while the traction battery remains high voltage, nominally over 800 volts. Translation: Tesla now runs two serious electrical worlds inside one vehicle, the high-voltage traction world, and a 48-volt low-voltage world OS. And when you do that, you create a whole new design space. Because the low voltage layer is where most of your day-to-day features live. And it's where you can simplify manufacturing, cut weight, reduce copper, reduce labor. And that's where the 48-volt secret hides. The simple physics that changes everything, here's the simplest equation in this entire story. Power equals voltage times current. So for the same power, if voltage goes up, current goes down. From 12 volts to 48 volts is a 4 times increase. So for the same power demand, current drops by 4. That's the difference between a thick, heavy copper cable and a thinner, cheaper run. It's the difference between a harness you have to wrestle into place and a harness you can route cleanly. It's the difference between heat buildup and comfortable margins. Now, that sounds like less metal, but what 48 volts really does is this. It changes what you can afford to build. Because once you're not spending your entire budget on copper and packaging, you spend it on architecture. And architecture is where the silver bomb is hiding. Before you call this Tesla being Tesla, you need to know something. The auto industry tried to escape 12 volts before. In the late 1990s and early 2000s, engineers pushed a 42 volt, 36 volt class transition. It sounded like the future. It sounded inevitable, and it died. Why? One reason was infrastructure. A Power Electronics News retrospective notes that the 42 volt bus was considered as a replacement for the entrenched 12 volt system, and there was just too much infrastructure, particularly batteries, tied to 12 volts. But the darker reason was physics. A Tektronix industry overview on switching to 42 volts warns that current 14 volts designs won't automatically work at 42 volts. Even simple fuses will not migrate, and that connectors, circuit breakers, and relay contacts may not be optimal at the higher voltage. Then it lands the punch. It cites research suggesting 42 volts arc energy can be 50 to 100 times higher than in a 14 volt system. And arcing can generate extreme temperatures and even ignite materials or melt metal. So the 42 volt dream ran into a brutal truth. You can't just raise voltage and keep the same cheap parts. You have to redesign the ecosystem. And redesigning the ecosystem is expensive. So the industry delayed. Then hybrids arrived with high voltage traction systems. Then efficiency improved. Then suppliers found ways to squeeze more out of 12 volts. And the big switch never happened. Until now. Because 48 volts didn't come back as a replacement first. It came back as a supplement. Power Electronics News notes that with increasing electrification, 48 volt systems have been exploited in new generation cars, often supplementing the existing 12 volt distribution, so more motors and appliances can draw current without disrupting the main activity of the drivetrain. That's the key lesson. 48 volts survived as add-on tech. But Tesla is doing something sharper. Tesla isn't just adding 48 volts next to 12 volts. Tesla is replacing the entire low voltage backbone with 48 volts. That is a standards move. And that's why this time is different. The real secret, Tesla is rebuilding cars like data centers. The biggest misunderstanding online is thinking 48 volts is about more power. In an EV, power isn't scarce. The traction battery has more than enough. So why bother? Motor 1 points out that in an EV, you already have high voltage available, which makes the motivation less obvious and raises the question of the point beyond design choices. And that's exactly where you need to look. The point isn't power. The point is architecture. In a 12 volt legacy vehicle, the harness is a spider web. One huge loom with branches everywhere, crossing the car, feeding dozens of subsystems. In a zonal vehicle, you stop thinking one harness. You think nodes. You place local control modules near where the loads are. Door zones, front zone, rear zone, cabin zone. Short runs, local decision making, high-speed data links. This doesn't just reduce copper, it reduces human labor. Because long, complicated harness routing is labor. Clipping, tying, routing, testing. Zonal architecture is assembly efficiency. And once your car becomes a cluster of nodes, here's what happens. You increase the number of interfaces. You increase the number of connectors. You increase the number of protected power paths. You increase the number of power conversion points. That is the silent trade. Fewer long copper runs, more touch points. And touch points are where silver lives. Now, let's talk about the moment 48 volts stops being nice and starts being required. Steer by wire. This is the kind of tech people assume is futuristic fluff, until you realize it's one of the most expensive mechanical systems in a vehicle. Steering columns, shafts, universal joints, packaging constraints, crash structures. Cybertruck's 48 volt system enables steer by wire, and Motor 1 calls it the first production car without a traditional steering shaft. Read that again. No traditional steering shaft. That's not a feature. That's a structural redesign. And Motor 1 notes the Infiniti Q50 offered steer-by-wire, but still kept the traditional column as backup, while Cybertruck does not. So why does this matter for the 48-volt story? Because steer-by-wire demands fast response, high reliability, and serious electrical muscle without instability. A steer-by-wire rack is not a tiny motor. It is a safety-critical actuator. And Tesla's own manual says the 48 volts low-voltage battery provides redundant power for critical systems, such as power steering. That is Tesla literally designing a separate electrical lifeline for steering. This is why I don't buy the idea that 48 volts is just for smaller wires. 48 volts is also about making certain safety-critical actuators possible in a clean architecture. And here's the uncomfortable implication. Once one OEM proves steer-by-wire can ship at scale without a traditional column, the pressure to copy isn't just cool tech, it's packaging advantage, manufacturing advantage, service advantage, and that means the 48 volts backbone becomes more defensible. Not because it's trendy, because it enables designs that are hard to do cleanly in the 12 volts world. Now, if you're thinking, okay, but Tesla can't just replace every legacy rail overnight. Correct. Motor 1 points out it's hard to know exactly what is and isn't 48 volts on the Cybertruck, and it notes Tesla's head of low-voltage electronics said the audio amplifiers are 24 volts, and the Cybertruck has provisions to be jump-started by a 12-volt battery if the 48-volt battery dies. That is a wild detail. It tells you the transition is messy. It tells you Tesla is already managing multiple rails. 48 volts is the main low-voltage backbone, but some subsystems still living on lower rails. Motor 1 also notes that the parts catalog suggests some 48 volts components were designed specifically for the truck, like window regulators, labeled 48 volts, while other parts may be shared with other models. Translation: Tesla is in the middle of an electrical migration, a controlled evolution, and in migrations, interface components are everything, because you're bridging old and new, you're translating between rails, you're protecting sensitive electronics, you're managing safety. Migrations multiply connectors, they multiply protection, they multiply the touch points. Which brings us back to silver. It says, Tesla engineers and Musk claim they reduced the weight of the wiring harness and the number of wires crossing the car. But it notes that's also thanks to a new Etherloop data system. That is the deeper story. This isn't just voltage. It's voltage plus data architecture. It's power distribution plus network topology. In other words, Tesla is treating the car like an integrated electrical platform, not a collection of parts. And once you go there, you don't just reduce wires. You redistribute complexity into nodes, which increases the number of interfaces that must be reliable. That's where the silver story lives. Not in a vault, in a connector. Here's where this story turns from nice to violent. The 12-volt world is forgiving. You can be sloppy, you can under-engineer, you can use cheap connectors, you can rely on brute force copper. 48 volts is less forgiving. Texas Instruments notes that moving from 12 volts to 48 volts increases creepage and clearance requirements, which impacts connectors, wire harness design, and PCB layout. That means the space between conductors matters more. The insulating geometry matters more. The connector design matters more. Because at higher voltage, electricity is more willing to arc. Motor 1 puts it plainly. 48-volt systems require stronger connectors and shielding to reduce the chance of arcing. Arcing is not a small problem. Arcing is literally electricity turning into a cutting torch for a fraction of a second. It pits contacts. It oxidizes surfaces. It creates resistance. Resistance creates heat. Heat accelerates failure. Now listen to Tesla itself, because Tesla is unusually blunt about this in its DIY documentation. Tesla's Cybertruck DIY guide warns, assume low voltage components are always energized. And because the 48 volts low voltage system operates at a higher voltage than a typical low voltage system, There's an increased risk of personal injury, arcing, or component damage if components are handled improperly. That's Tesla saying. This is not a toy system. So when you move the entire low voltage ecosystem from 12 to 48, you force a quality upgrade. And quality upgrades don't happen on slides. They happen in materials,